All right. Well, hello, chemists, and welcome back to this week's masterclass. All right. So this week, chemists, what I've been asked to do is have a chat with you about Arenes. It appears that quite a few of you are studying Arenes, aromatic chemistry, and a few questions came up. All right. So what I wanted to do was well, a couple of things. Number one, I want to talk about what an arene is, number one. And then number two, I wanted to talk about the stability of arenes. All right. And we'll talk about sigma bonds, pi bonds, delocalized electrons, unhybridized p orbitals. All right. We'll do a past paper question on this one, which they just like to ask. All right. Where they basically try to figure out, do you know the differences between a double bond and a pi bond? Okay, so we'll do this one. So we'll talk about benzene, we'll talk about the stability of benzene, and then towards the end, what I thought that we would do is have a look at naming arenes. Okay, so towards the end of the help session today, what I'll do is I'll talk about the naming of arenes and when to use phenyl and when not to use phenyl. Okay, so here we go with this one. Now, this week, chemists, is a slightly different setup because I seem to have a little problem here with the ink on the page keeping up with me. So I'm on Microsoft OneNote, and for some unknown reason, the ink doesn't always stick to the page. I don't know why. The wonderful folks at Microsoft are trying to figure out why this is happening. Maybe it's just me. So anyway, if you know why the ink is not sticking to the page, then do me a favor to send me an email explaining this one. All right, and then we're good to go. But here we are then. All right, so benzene. Okay, benzene. All right, and I'll turn my digital pad on right here so you can see what's going on. It's this structure on the left-hand side here. Now, what it is that it's a six-membered ring. All right, so you know, 6 carbons in a row, carbon, 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 carbon going around. And so this is benzene like this. All right, now you know that carbon is tetravalent, which means that if I scroll down a little bit in my notes here on this bit here, right, carbon is tetravalent, meaning it wants to form 4 bonds. Well, you knew that from probably GCSE, all right? And so this is the reason why I've drawn carbon like this up here, carbon with 4 bonds coming out of it, a single double bond between one carbon and the next carbon, and a hydrogen. All right, coming up the top there. So done, ding, 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 ding. Yes, done all that. Good. Okay, right. Now, just to check a few things there. Now, what you've got to keep in mind is that the very first bond that you put down when you're drawing a structure, a displayed structure, you know, where you show all the bonds, for example, the very first bond that you put down is a sigma bond. All right, so you may have just been writing down single bonds, but in actuality, what they are is that they are sigma bonds, okay? So a sigma bond here is nothing more than a single bond, which is why down here what I've done is I put in the sigma bonds, all of the single bonds. And so carbon-carbon is a single bond, that's a sigma bond. The carbon to hydrogen is a single bond, that's a sigma bond, right? Now, having said that, the next bond that you put in is a pi bond. And so because we're talking about a double bond here, what you've got is that you've got a single bond over here, and then indicated in red, what I've got here is I've got a pi bond. So a pi bond is what, yes, you would tend to think is a double bond, all right? A triple bond would be 1 single and 2 pi bonds. Now, got to keep this in mind, right? So a single bond is just nothing more than the sharing of a pair of electrons, one from each atom. And so your single bond would be a sigma bond. Anything else on top of that, like if you're doing a double bond or a triple bond, those extra bonds that you put in to make the double or the triple bond would be pi bonds. Okay, so having said that, then chemists, coming over here on this bit, okay, I know we had a problem with the ink today sticking the page, so I wrote everything out beforehand. All right, I've now come to draw my benzene ring. So my benzene ring, like I said over here, is a 6-membered carbon ring, okay, with alternating pi bonds, like double, a single and sigma pi bond there, sigma bond, single bond, double bond there. So this is a pi bond right there, a single and a pi. You get it, right? So the thing is then, what I'm doing is I'm avoiding the word double bond, okay? Because benzene rings, they don't have double bonds in them. All right, so you got to be a little bit careful about this one, okay? When you think of a double bond, you're thinking of something like an alkene. An alkene is a double bond, a carbon-carbon double bond. Yes. In a benzene ring, which is a 6-membered ring with alternating pi and sigma bonds, they're not double bonds. And I'll get back into that in a minute, because what it does is that it just explains all of the chemistry. So here we are then with this one. I can draw the benzene ring like this, pi bond, sigma, or could I draw it like this, the next one across, where what I've done is I've just put the pi bonds in a slightly different position, but still got pi bond, sigma, pi bond, sigma, pi bond, sigma going around. Now, the question is, well, which one is it? Is it the one on the left or is it the one on the right? Now, the answer is it's both. All right, this is why I put this bin here for my math people here. They are equivalent structures. All right, they're equivalent structures because what you've got is that you've got resonance. All right, so resonance here is just where the pi bonds are moving around the ring system, okay? So what you see in the question is that you don't see these structures, all right? What you see is that you see a ring with a circle in the middle. And the circle in the middle, what it does is it indicates that you know to the examiner that these are not double bonds. In fact, what they are pi bonds, and the pi bonds can actually move around the ring. And this one is benzene, which is what they ask you at A level. Now, a long time ago, when I was a young chemist, all right, we used to call these aromatics. Now they're called arenes. And so the term aromatic came from when they discovered these, I think in like the late 1800s, they were coming from aromatic compounds like camphor oil, for example, all right? And so because they had a very pleasant aroma to them, they called them aromatics. Well, in actuality, they're not called aromatics anymore. What they're called are arenes. Now, see this structure here, with the alternating pi bonds, okay? Pi, sigma, pi, sigma. These are known as Kekulé structures, all right? Now, in your textbook, it does actually say, it's this story. It's one of these apocryphal stories which says that Kekulé fell asleep in front of his fire, smoking his pipe, and he dreamt of a snake biting its tail. And this is how how Kekulé came up with this structure, this alternating structure of pi bonds and sigma, pi bonds and sigma bonds going around the ring. Now, this one, this story has been discredited on two different fronts. Okay, one of them is, and I'll put the article on my website. I said I wouldn't promote anything, but this isn't a promotion. On my website, I'll put the article which talks about the fact that now they believe that Kekulé didn't come up with the structure like he did, number one. All right, it was other chemists that came up with it, but he's been given the credit for it. The other one is that, well, the story that Kekulé fell asleep in front of his fire, smoking his pipe, is also a little bit embellished. Okay, and the reason I say that is that if you look into the history of chemistry, what you notice is that during that day, during those times, how can I put it, recreational drug use was more accepted. And so Kekulé was a drug addict, okay? I think he was either high on heroin when he came up with it, or was it marijuana? But the point is that the story of him falling asleep in front of the fire is not true, based on the history that we know of that time and the work of other chemists. Okay, but we'll just go with the fact that we'll call these Kekulé structures. Now, having said this, chemists, what you got to keep in mind is that these are not double bonds. And I keep on mentioning this one because it explains the chemistry, which I'll talk about next week. Okay, so if I look then at carbon, we'll have a little look at the hybridization of carbon here. Okay, so carbon, as you know, carbon, the atomic orbital filling diagram is, well, helium 2s2 2p2 with two single electrons in it. I've indicated here with the yellow highlighter, right? Now, problem is there aren't enough single bonds in the carbon atomic orbital structure like this diagram to show three bonds. Because keep in mind, over here, chemists, I did need to have the ability to form three bonds: carbon, 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 hydrogen. So I don't know where you stand with the concept of hybridization, but if I look at hybridization now, when I tutor, I do mention hybridization because it explains a lot, like the VESPR diagrams that shapes the molecules, the molecular polarity, and everything else. And so, if you take chemistry at university, you'll get into hybridization a lot more. But here we go with a really shortened, well, I guess like a quick overview of hybridization. All right, is this one? All right, what I've got here then is I've got my atomic orbital diagram for carbon, and keep in mind that the 2s and the 2p are on the same energy level. How do we know? Well, they got the 2 in front of them, the quantum number 2 in front of them, right? So what I'm going to do is I'm going to promote an electron from the 2s orbital over to the empty 2p orbital, which I've indicated with my green arrow there, and my mysterious looking green electron. What I've done is I've moved this electron here over to this electron there. Now, you're thinking, the physical chemist is thinking, well, why exactly would I do this, Graeme? Well, because the electron, when it's paired up in the 2s orbital, what it has is it has electron pair repulsion energy. You got two electrons inside the same orbital. They go on to repel each other. Therefore, they're slightly higher in energy. If it moves over to the empty 2p orbital over here, then what you've got is a lowering of the energy. So this is the reason why you move the electron from the 2s over to the 2p. Now, keep in mind, and this is how I explain it to my students, is this: just because the room is empty doesn't mean that the room doesn't exist. Like, for example, when you leave sixth form college at the end of the day, you know all the rooms in the school, in the college. They may be empty, but they're still there. And the next day that you go into class to have a lesson, of course the room is still there. You're not surprised by this, right? Just because that room is empty doesn't mean that the room doesn't exist. Well, it's the same thing here. Just because it's 2p orbital in the 2p subshell is empty, it doesn't mean it doesn't exist. Of course it exists. And so therefore I can put the electron into it. Now, when I do that, what I do now is I form 4 single electrons, 1 per atomic orbital, right? As in 1 in the s and 3 in the 2p subshell, 1 in the 2px, 1 in the 2py, 1 in the 2pz orbital. So now I have the capability, the option of forming 4 bonds, right? Now, when I come over to here, and I take a look at this one, I need to form 3 bonds. Recall carbon, 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 hydrogen. For my sigma bonds, right? It's my single bond. And so what I'm going to do is I'm only going to use 3 of these hybridized orbitals, 1s and 2p's. And so you're thinking, make that a 2. All right, make this a 2. Should have been a 2. All right. You think what I've done then is I've used 1s and 2p orbitals. And so if your teachers taught you about orbital hybridization, this is where I always use the right-hand rule. Your thumb is the s and your p orbital are the fingers. And so if I use 1s and 2p's, then I've got an sp2 hybridized orbital. And so I've got 4 of them. So what I do is this, is I say, right, I'm going to take 1s and 3p atomic orbitals, mix them together, and I'm going to come out with 3 atomic orbitals on the same energy and of the same type. Okay, so what I've done here is this one here. What I said here is, look, I've got 1s and 3p and 2p atomic orbitals going in, all right? And so what I've done then is I've got 1, 2, 3 hybridized orbitals coming out. Now, because of that, what I've got is this. I can now say on this bit, yes, what I've got is I've got 1, 2, 3 atomic orbitals, which have been converted into 3 hybridized orbitals. This is where the single bonds come from. Now, having said that, let's see if I get my ink to actually sync here. I think it's doing something now. All right. The question is then, if I'm only using 1, 2, 3 of these sp2 hybridized orbitals, the question becomes, what do you do with the 4th one? There is an electron in the 4th atomic orbital here, right? So you're thinking, right, this electron in this orbital here, this orbital was not hybridized because I didn't use it in the bonding. I only used the first 3 atomic orbitals in the bonding. It's where I got the sp2 hybridization from. And this is how I got the 3 sigma bonds coming off the carbon. So this orbital at the end is unhybridized, which means that it's just a p orbital. And this one is where you can start to form a pi bond. So up here, you see my pi bond, my quote, second bond that I put in, avoiding the word double bond here. This is due to an unhybridized p orbital. Now, think we covered everything on my notes here. I think we have. So by the way, chemists, if you're on my master class in A-level chemistry, all right, email list. I do email out recordings of these lessons if you have missed the live stream, and you can also access all of my notes as well, because I just share my OneNote with you. All right, so this then is where the benzene comes from. So benzene, you're thinking benzene, chemists, they aren't double bonds. Oh, no, 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 no. They're not double bonds. They are pi bonds. And a pi bond is a bond, and I'll show you the graphic right now, is a bond, this is the graphic that I wanted, hold on, right here. This one here, I'll show you this one nice and large now so you can see and give the ink time to update. Look, the pi bond, what we're talking about quite simply then is this. It is the unhybridized p orbitals left over from the hybridization of the carbon. 1, 2, 3 bonds in carbon, like I said on the previous tile, sp2, all right, which means that the one that's left over is your unhybridized p orbital, and these overlap. Okay, and these orbitals overlap, and so therefore the electrons in those orbitals can actually, they can circulate around the ring, and because they can circulate around the ring, you now have what's known as resonance, which is where these pi bond electrons are moving around the ring. Now you're thinking, great, problem is, where's the evidence for this, right? I mean, you say, well, Graeme, just because, you know, you put some notes upon OneNote and everything else, yes, but where's the evidence for this? I mean, how do you know? Well, like I said, this one here, this is from theory what we know it to be, all right? So this one here is from theory, from molecular orbital hybridization, it's this. And then if I take a look at this one, okay, hold on. Hold on, chemists. This one, this one. This one here. This is what I needed. Look, on this one, there's some actual data that they can use. All right. And so you're thinking, well, the first thing is that you've got this, see over here, see this cacule structure over here on the left-hand side. You got this, right? Now, again, we said that these pi bonds can move around the ring. And so if you use X-ray crystallography, what you find is this, is that you can measure the bond length, yes, and you find out that the bond lengths are all the same length. So they're not the length of a single bond. No. They're not the length of a double bond. No. They're the length of a bond and a half. So all the bonds in a benzene ring and an arene are a bond and a half length long, which confirms the fact it can't be double, single, double, single, double, single going around the bond, because around the ring, because otherwise what you would have is, well, you wouldn't be able to measure the bonds, wouldn't you? Because this is a double, this is a single, this is a double, this is a single. Oh, no, 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 they're all a bond and a half, which means that the bonds, the pi bonds, must be rotating around the ring. And so this is how we can confirm the fact that you have these pi bonds in these unhybridized p orbitals moving around the ring. Why? Because of the bond length, right? Now, something else to keep in mind is this one, all right, is that the benzene molecule is flat. If it was double, single, double, single, double, single going around the ring, well, then it wouldn't be flat. It would be kind of like scrunched up, wouldn't it? Like, I don't know, like a flower, because all the bonds are different lengths. But no, because they're the same length, they're all flat. So benzene is a flat molecule. Now, the reason I mention this, chemist, is because this bit does become important when you start looking at the physical properties, like when you start looking at the boiling point and the melting point of benzene, okay, which we'll do next week. Right, now, if I take benzene, benzene is flat, all right? If I take benzene then, and then I compare it to cyclohexane, you see what the difference is. You see, look, cyclohexane is all single bonds, right? It's just carbon, 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 carbon going around the ring. It is a single bond. Now, because it's a single bond, you can rotate the atoms around those single bonds. There's nothing locking them into place. Like, you know, maybe your teacher's done the one with a pi bond. You know, if you've done alkenes, if you've done easy isomerism, okay, like SIP rules, you're thinking you can't rotate around that double bond. And so therefore you have two different isomers. You have the E and the Z isomer, right? Well, benzene is flat. You can't rotate around the carbon-carbon double bonds. And so therefore it's flat as compared to cyclohexane. Cyclohexane is all single bonds. Yes, you can float. You can rotate around the carbon-carbon bonds, and you can get them into two different conformations. Number one is the boat conformation, which I've drawn here, right there. This is my boat conformation, like this. You can float it, you know, think of a boat floating on water like this. And you can also twist it into the chair conformation. All right. So physical property of benzene is that due to the bonding in benzene, it's flat and everything is locked into place. Now, what they'll ask you to do, by the way, is compare benzene to cyclohexane, the physical properties, but we'll do that next week. Now, the next thing that they're going to ask you about then is the stability of benzene. Now, this one, if you look at it and go, I don't know, Graeme. But on the other hand, if you think, yeah, okay, I get it. So for example, look, cyclohexene, all right, is a 6-membered ring, yes, with a double bond in it. And you can hydrogenate across the double bond. You can add hydrogens across that double bond. And when you do, you go back to cyclohexane, and the energy released is minus 120 kilojoules per mole. So you're thinking, right, one double bond is minus 120 kilojoules per mole. So therefore, two double bonds, logic, you would say is minus 240. 2 times minus 120 kilojoules per mole. Right, and it is. But then if you come down to the theoretical model, the theoretical molecule cyclohex 135 triene, where you would think, hold on, it's 3 of these double bonds, 3 times minus 120 is minus 360, right? Theoretical. It isn't. It's actually lower. All right, so what they're going to ask you to do, and we'll do a past paper question now, is this one. They'll say, explain why you've got the difference in enthalpies. Well, this is the chart, the diagram you need to know. So this one here, I've got cyclohexane as my base, and I'm saying if I'm cyclohex 135 triene, okay, well then I'm going to release 360 kilojoules of energy if I hydrogenate across all 3 of these theoretical double bonds, right? Now, if I've got benzene, well, benzene only releases 208 kilojoules to take it back down to cyclohexane. And you're wondering, well, why? what's the reason for that, right? The reason for that is because, as we said in the previous tile, these delocalized pi bond electrons, the overlapping p orbitals, right? Take a look. On this one, these pi bond electrons, they're locked into place. They can't go anywhere, all right? This one down here, I've got pi bond, single, pi bond like this. Yes, you can get a little bit of resonance, like you do get overlap, all right, on each of the carbons. You've got the unhybridized p orbital, so you do get a bit of overlap, right? You're thinking, yeah, minus 240-ish, okay. But with the cyclohex 135 triene, yes, what you've got is that you've got overlap of all 6 carbons, right? You've got overlap of the p orbitals in all 6 carbons, which means that these pi bond electrons can move around the ring. And because they can move around the ring, what you've got is that you've got some more stability than what you should have. So it should be 360 kilojoules. It's actually 208, which means that you've got a little bit more stability than what you should have. 360 minus 208 is 152, right? Now, if they ask you this, and they're going to ask you this on the exam, chemist, right, is this. You say, what's the reason for this stability? Well, simple. It's pi bonds. Please don't write down double bonds, write down pi bonds. It's pi bonds, and it's delocalized electrons, meaning they can move around the ring. All right, got here, around the ring in this ring system, the overlapping p orbitals, and it's resonance stabilization. So resonance just means that you can have more than one structure, and stabilization means it's more stable than what it should be due to the resonance. Okay, so 2 key buzzwords here, right? Delocalized electrons and resonance stabilization. Talk about pi bonds. Don't write down double bonds. Write down pi bonds. Okay. Don't use the Kekulé structure. Use the one with the ring in it, because then this indicates to the examiner that you know for a fact that this is not 3 double bonds. You know that this is a ring system with a delocalized pi bond system indicated by the circle inside the ring, right? So this is the stability of benzene. All right, so hold on, get back to here. Now, chemists, what I wanted to do is I wanted to do a past paper question with you. Now, like I said, bit of a issue with the ink on OneNote. I don't know why it's doing this. I don't know. So anyway, wherever you are on the road listening in, if you happen to know the reason why, always please let me know. All right, so here we are then, typical past paper question, all right? Now, I picked these because it doesn't matter what exam board you're on, you know, AQA, Edexcel, OCR, Cambridge, whatever. They're always going to ask you this question. Why? Because at testing, do you understand about resonance stabilization? Do you understand about pi bonds? All right, it says, use these data to show that benzene is 152 kilojoules per mole more stable than the hypothetical compound cyclohexane 135 triene. It doesn't exist. It's known as benzene. Okay, so here we are then. Here's the logic, like we did in the tile with the notes on it. Okay, my 135 triene should be, well, if one pi bond is minus 120 kilojoules per mole, well, you would think if I had 3 pi bonds in it, it would be 3 times minus 120 kilojoules per mole, which is minus 360, right? Yeah. Benzene, down here, when you hydrogenate the pi bonds in benzene, you only release minus 208 kilojoules per mole. And the difference from that is minus 152 kilojoules per mole, which is due to the resonance stabilization. So a pure chemist, what I got here on the left-hand side is, this is my benzene ring, my 6-membered ring like this, and I've got the overlapping p orbitals here, and I've indicated the fact that the pi bond electrons can move around the ring. Yeah? Now, let's see, part 2, state in terms of bonding why benzene is more stable than cyclohexane 135 trine. Now, chemists, on this one, what they're looking for is they're looking for buzzwords. All right, so looking for buzzwords. What you have is you have a delocalized pi bond. Now, did you notice how I've referenced specifically delocalized pi bonds, and I said due to unhybridized p orbitals? And so whichever spec you're on, you should have kind of a fundamental understanding of hybridization of atomic orbitals into molecular orbitals, all right? I have one orbital left over which did not get hybridized. They're overlapping, which means that the pi bond electrons are free to move around the ring, yeah? So this one, make sure this one, chemist, is in your notes, okay? Now, let's see, moving on to part B. 3 carbon-carbon bonds are labeled in the structure shown. These bonds have different lengths. Yes, they would be. All right, write the letters W, X, and Y in order of increasing bond length. So chemists, look, when you start doing these past paper questions, right, you got to start thinking, yeah, I wonder why are they asking me this question? The teacher is asking you this question because he wants to know, or she wants to know, do you understand that the bonding that takes place inside benzene involves delocalized pi bonds? Think back to the X-ray crystallography bit that I talked about, right? So a single bond would be the longest, so therefore this would come last. Let's say a double bond would be the shortest, this would come first. And then you're thinking in the middle then would be the pi bond, which is indicated in the ring system here. It's what this circle means inside my 6-membered ring. And so this one then would be about a bond and a half. Yeah, so it goes in single, it goes double, bond and a half, single, right? Now, coming down to this one. Now, this one, the reason why, chemists, I put this one in is because, get this nice and centered on the page here, is because it's a bit tricky. It is. It's a little bit, it really tests you understand what a conjugated system is. So conjugated pi bonds, what the system is this. What it means is this, is that you've got pi bond, sigma, pi bond. This is your conjugated pi bond system, like the bare minimum that you can have. So therefore, you can, the pi bond electrons, they can start to move between one bond and the next, okay, because you've got the overlapping p orbitals. And so here we are on this one. It says, use the enthalpy of hydrogenation data given opposite, actually on the very first question, to calculate a value for the enthalpy of hydrogenation of cyclohexane 1,4-diene. Right, now on this bit, question, on this bit, chemist, do you see that the 2 pi bonds, they're nowhere near each other? So it goes pi bond, sigma, sigma, pi bond. They're nowhere near each other. So therefore, you can't have overlap of the p orbitals, because to have overlap of the p orbitals, what you would need is pi, sigma, pi. So those p orbitals actually do have the chance to overlap. This one then is just 2 times minus 120, which is minus 240 kilojoules per mole, like this one. And then the next one down, it says predict the value for the enthalpy of hydrogenation of cyclohexane 1,3-diene. Now, a little bit tricky. And the reason why I put this one in is because some students would think, oh, well, it's well, the same thing, right? So therefore it's 2 of these pi bonds, so 2 times minus 120 is minus 240. No, because look at the distance between the bonds. It goes pi, sigma, pi, right? So therefore, the value, well, it must be above the value for a 1 pi bond, minus 120. It's got to be below the value of 2 pi bonds, which is minus 240. It's about somewhere in the middle. And the reason for this one, again, is you're thinking it's your pi bonds, it's resonance stabilization, the fact that the electrons in those pi bonds, these pi bonds here, they can actually start to move around the ring from this pi bond over to this pi bond. I'm not saying all the way around the ring, but just where the pi bonds overlap, the pi bond, sigma pi bond, you get the overlapping of the p orbitals, right? Now, this is it. Then explain your answers to part 1 and part 2 in terms of bonding in these 2 dienes. Right, well, what I said was, because I obviously did this one earlier, problem with the ink today, is, yeah, in the cyclohexane 1,4 diene, it's not conjugated. It's not pi, sigma, pi. So therefore, there isn't resonance in the ring. So therefore, you don't get resonance stabilization. On the other hand, the 1,3 diene is resonance stabilized because it goes pi, sigma, pi bond, right? The p orbitals do overlap. Therefore, you would get some more stability for the 1,3 diene. Now, this bit, so far, hopefully, has introduced you to the concept of arenes. All that arenes are ring systems with pi bonds in them. Okay, not double, ring systems with pi bonds in them, conjugated pi bond systems. We've looked at the historical bit about benzene, and I'll put this on my website. It wasn't discovered by Kekulé. There's a lot of information showing that he didn't actually come up with this bit. And then we looked at the stability of benzene, which becomes important when we do Friedel-Crafts acylation reactions, okay? So you're thinking the stability of benzene has to do with the resonance stabilization you get from the conjugated pi system. It also means that because the way it's bonded inside the ring, that you've got flat benzene rings, and so therefore they sit on top of each other, like stack on top of each, like layers. And so therefore this affects the physical properties of arenes, which we'll talk about next time, all right? As in melting point, boiling point, and solubility. But what I wanted to do is I wanted to have a chat with you about naming arenes. And so this bit, no, on the naming arenes bit, okay, what I wanted to do is I wanted to do 2 things. I wanted to explain, obviously, how to name systems based on benzene, but also explain to you how to name a system when the benzene mysteriously becomes a phenyl, air quote, group, okay? And how to number the rings. So I want to do that. Next week, what I'll do is have a chat with you about this mysterious thing called ortho-meta-para. Like you may see this in the older textbooks, like ortho-meta-para is used in front of the name. You're the modern chemist. You would actually number the carbons, the locant for the ring on the ring systems where the substitution groups are. But I'll do that next week because that dovetails into when you do Freeland-Craft acylation reactions, why you get more than one product. Like you get a predominant, like a major product and two side products. And I'll tie that in to the one question they always ask you on the exam. All right. And you wonder, well, why is it this? And there's a very simple reason for it. Okay, but I'll do that next week. All right, then, chemists, here we are. So look at this one then. Now, what I'm saying is this. Arenes used to be known as aromatics. And they've been around with us for a very, very long time. And then the chemists, we all moved on to the IUPAC nomenclature. But there's a bit of the naming that is like stuck in the past that we can't get rid of. All right, like for example, CO, we know as carbon monoxide. Technically, it should be carbon oxide, but we all call it carbon monoxide. Just something which is like stuck with us. So on this bit then, chemists, what I've done here is on this bit is I've done this. Look, I've listed 1, 2, 3, 4. The 4 foundational structures, the 4 bases that everything else is based on. Now, when I say base, I don't mean acid and base. I mean like the fundamental structure, like the starting point of all of the naming. And this comes from, again, antiquity. Like, you know, it's been with us like such a long time, we can't get rid of it. So on this one then, what I've got up here is I've got, on the left-hand side, I've got methyl benzene. So methyl benzene is obviously, look, again, circle in the middle of the ring. All right, my methyl benzene is where I stuck an alkyl methyl onto benzene. It used to be known as toluene. This is methyl benzene. Or I can put a halogen onto a benzene, and this would be chlorobenzene. Logic. Now, next one across then, I put a nitro group. See, it's an NO2 here. I put a nitro group onto a benzene. This is nitrobenzene. And the last one, this is an update. For you modern chemists, I would know this as benzoic acid. You know it as benzene carboxylic acid, right? Okay, so having said that, chemists, here we are. Keeping in mind that benzene is my base. If I add a halogen to it, it's going to be chlorobenzene. And if you add a nitro group to it, it's going to be nitrobenzene. And you're thinking, yeah, okay, that kind of makes sense. And then you look in your textbook and you say, well, hold on, what on earth is this? I mean this right here. This is phenylethene. And you go, yeah, but hold on. I thought you said it was benzene. When is it phenyl? I mean, first off, why is it phenyl? And how do you know when to call it benzene or when to call it phenyl? Well, the answer is it has to do with the priority of the substituent groups, which I'll get into next time, all right? But this is how I explain it to my students. I say this, right? If I look at this one, if you're trying to rationalize by this molecule on the left-hand side, this is phenylethene. You think, right, start off, think of the base compound, it's ethene. Now, could you replace a hydrogen with an alkyl group? Well, you say, yeah, Graeme, like you see this hydrogen here coming off right there. Yeah, I'm going to replace this with a methyl. I'll just use methyl as my alkyl group. I go, yes, 1, 2, 3 carbons. This would be propene. Right. Now, on the other hand, can you replace a hydrogen with a ring system? Now, the ring system, use a new word, chemist. This is aryl, A-R-Y-L. So you're thinking, can I replace the hydrogen over here and can I put a benzene on it? Yes. Because if you can replace the hydrogen, put an alkyl on it, then you can put an aryl group on it. And because you can do that, the benzene is known as phenyl. Because, and I'll put this I'll talk about this one next time. If you look at the priority system of the substituent groups, then what you've got is, well, you know, the carboxylic acid and the alcohols are at the top, and all the way down the bottom are like the alkyls and the aryl groups. This phenyl is a lower priority than this alkene here, and so it's why it drops down to phenyl ethene, right? So take a look then at these. And this is exactly what I mean. Like, see this one, like phenylamine. All right. Now, I don't know if you've done amines yet, but you're thinking, right, phenylamine. Well, I've got my if I start off with ammonia, I've got NH3. And then ask yourself, can you replace a hydrogen on ammonia with, say, a methyl? And you go, yeah, I'd have methylamine. Well, then you can replace that hydrogen on ammonia with an aryl group, and the benzene would be demoted down to a phenyl. This is known as phenylamine. Okay. And if you look at all of these molecules going from left to right, we've done phenyl ethene, going from left to right, then you're thinking, yeah, here is my 1, 2, 3, 4 carbons, butane. Can I replace a hydrogen on butane with a methyl? You're saying, yeah, you'd have 2-methylbutane. Well, then you can replace it with a benzene ring, which becomes a phenyl, and you have 2-phenylbutane. And the logic just carries on, right? Like, you know, this is my ketone. All I've done is I've replaced a methyl group, an alkyl group, with an aryl, and I've got phenylethanone. All right. And it just keeps on going. Now, this is the logic then of when to know it's benzene and when to know it's phenyl. All right. Benzene is when it's the base. Okay. And phenyl is when you have a higher priority functional group. It then drops down to being phenyl, because you're thinking, yeah, all I've done is on my high priority functional group is I've just taken off a hydrogen and I've put a phenyl, a benzene in its place, right? So question then becomes, well, what happens if you have more than one substituent group? Again, chemists, he's thinking, well, to be honest, it's the same thing. Oh, no, I've got ink coming in here. Maybe my pen was touching my board there. I don't know. Right, look, it's the same thing as when you had more than one substituent group on an aliphatic, like a straight chain carbon, you know, like, I don't know, pentane or hexane or something. You had to number the carbons, and you had to number the carbons using the lowest numbering system possible, right? Like your teacher probably taught you, like, you know, number from left to right, and then number from right to left, and whichever numbering system gives you the lowest numbers, this is the one to use. So in red here, all right, well, I put chlorine as number 1, because obviously one of them has to be number 1. And if I go clockwise, this would mean that the chlorine in position 3, this would be 1,3 dichlorobenzene. 1, carbon number 1, 3 dichlorobenzene. I didn't do it going counterclockwise in blue, because then you'd end up with 1,5 dichlorobenzene. Now, the next one then, a little bit more tricky. Take a look. I've got a benzene ring, I've got a chlorine on it, and I've got an ethyl. So keep in mind, you see this funny looking little stick thing here, right? You're thinking, yeah, there's a carbon bond, and then this is the 2 carbons of the ethyl, and here's my carbon bond, right? So again, you're thinking, well, which one would I number as being number 1? Is it going to be the chlorine or the ethyl? Like over here, and this one on the left, you're thinking they're both the same thing, right? The chlorine and chlorine, so it doesn't matter. But this one, again, you just default down, right? Look back into your notes about the naming of organic compounds. You're thinking, yeah, this would be 1,3 ethyl benzene. Why? Because you list them in alphabetical order. Now, I did say I'll mention this next week when we talk about reactions of arenes, okay? But this is my A-star chemists, as in all of you, right? My A-star chemists, all right? They'll start giving you mechanisms, which we'll do next week. And all of a sudden, you know, you start coming up with like, well, they say it makes this product, so what's the other possible product it could make? Now, this then is the ortho-meta-para naming system. Now, I'm an older chemist. I know it as the ortho-meta-para. You're the new modern chemists. You'll know it as the 1,2, the 1,3, and the 1,4. Okay, so what I mean by this one is, you see this one, all right? I got, obviously, now look, nitro benzene, the NO2 nitro benzene, okay, is one of the bases that we talked about, right? So you got carbon number 1, and let's just say that I had a substituent I put on carbon number 2. Carbon number 2, to an older chemist, the 1,2 combination is known as ortho. You know it as 1,2. This would be 1,2 disubstituted. Over here, I got something in carbon number 1, I got nitro on carbon number 1, and I got chloro on carbon number 3. This, to me, would mean meta, all right? To you, it would be 1,3 disubstituted. Now, over here then, last bit, carbon number 1, carbon number 4, I would know this is para, you know it as 1,4 disubstituted, okay? Now, next week, I'll talk about ortho-meta-para directors and how they affect the outcome of a reaction. So if I come down to here then, all right, take a look. If I wanted to name a disubstituted arene then, okay? Well, first thing I'm going to do is I'm going to start with my base. Now, recall I said methyl is one of the bases, like the methyl benzene, the nitrobenzene is another one. The other one is benzene carboxylic acid. And so, again, I'll have to chat about this next time. The nitrobenzene is a high priority. And so therefore, the nitro group. So you're thinking nitro would be number 1 and chloro would be number 2. So therefore, this would be nitro and then chloro. So start with number 1, it would be 1 nitro, 2 chloro benzene. Now, the question becomes, well, hold on a minute, hold on. How come you didn't do it in alphabetical order? Because the nitro is the highest functional group out there. It's the highest priority functional group. So this becomes 1 nitro, and then you list everything else, 2 chlorobenzene, right? Okay, so coming down here then, chemists, what I got down here is I got some examples for us to go look at. All right, like I said, I had a problem with the ink this week, so I just put the graphic in for us to go look at. So first one then, again, carbon number 1, carbon number 2. This would be 1, 2. These two sticks are methyls, 1, 2 dimethylbenzene, like this. Okay, now this one, this was A on B. This is, okay, I've got methyls in. Now, what you need to do is number them, chemists. And again, when you number it, you've got to make sure that the substituent groups have the lowest number possible. So this would be carbon number 1, carbon number 2, 3, 4, 5, like this. And so this would be 1, 2, 4, 5. List the locants, right? Tetra, 4, methyls, those stick things coming out, benzene. Okay, now going on to this one then. Okay, now this one, slightly confusing, chemists, because this is a methyl group on the left-hand side, and this is an ethyl group on the right-hand side, this little stick thing here. All right, now, I would think the base is methyl, so this is carbon number 1, 2, 3, 4, right? Because we're going off the fact that methyl benzene is one of the bases that we talked about. And so you've got a methyl in carbon number 1, and you've got an ethyl in carbon number 4. So I would call it 4-ethyl 1-methyl benzene. Why? Well, because I'm going to list it in alphabetical order. Why? Because the two alkyl groups, okay, it's not like there's a nitro on one side and an alcohol on the other side. There's 4 nitrile groups. So I would then just say, because they're both alkyl groups, list them in alphabetical order, 4-ethyl 1-methyl benzene. Okay. Now, D, we've done D. This is my phenyl ethene. Did this one before. Recall I said all I've done is I looked at the functional group, in this case the alkene, and I said, can I just replace a hydrogen and put a methyl group in? Yes. Well, if I can do that, I can replace the hydrogen and I can put an aryl group in, like benzene, but it demotes down to being phenyl. Okay. Now, talking about ones that are a little bit more tricky, right? Take a look at this one then. All right. Right here, what I've got is, now this is how I would name it. We have a choice. You've got 1-methyl ethyl benzene, okay, or we've got 2-phenyl propane. Either one would be correct. On this one, chemists, I would go with the first one. And the reason is because if it was just a methyl coming off this would be methyl benzene, right? If it's just a methyl coming off. If it was an ethyl, then it would be ethyl benzene. Now, what this is saying then is that you need to number the chain going down like always. And carbon number 1 on the chain is a methyl group. And this would be 1-methyl, this methyl here, ethyl, the chain, benzene, okay? This one here is very similar to what we've done. Okay, this is 2-phenylbutene. All right, now again, if I just take a look at this one, Cam, you see like this chain here, 1, 2, 3, 4. If this phenyl group wasn't there, you just call this butene. And all I've done is I've replaced the hydrogen with a different group. Now, if it was a methyl, then you would call this 2-methylbutene. So just because you put a benzene ring in, it now becomes 2-phenylbutene, right? So, I think we've got time just for a few more. All right, so hold on. This one, G, is a good one. Okay, chemists, carboxylic acids are the highest ranking priorities, substituent groups, right? So if this ethyl wasn't there, then you would call this benzene carboxylic acid. Now, what I've done is I've put an alpha group on it. So this is carbon number 1, has to be, because it's the highest ranking priority group. This is carbon number 2. So therefore, this is 2-ethyl benzene carboxylic acid. All right. You see the one with the phenyl right there. Is this one of my new? I saw this one of the base keys to put in. Hold on. So this one here, right? Phenyl is just a benzene ring with an OH on it. It's one of the base compounds that we can do, right? So Chloro is in carbon number 2 position. So this would be 2-chlorophenyl. All right. Over here is your ester. All right. It is phenyl. I think by now, hopefully you're getting the idea here. Okay. Now, J. J is a little bit tricky because you've got obviously a carboxylic acid group in carbon number 1, 2, 3, 4. And so therefore, this is 1,4-benzene dicarboxylic acid. Now, the reason I say that is because if this other acid group wasn't here, it would just be benzene dicarboxylic acid. All right. Now, we've got a choice of 1,4-benzene dicarboxylic acid or benzene 1,4-dicarboxylic acid. I would actually go for the second one. Why? Because benzene, and then you got 1,4, the two carbon groups right there, two carboxylic acids. So it's this one. All right. This is just your amine. Now this one, all right, a little bit tricky, Kim, because look, this is carbon number 1 on the ring. It's carbon number 2. This is carbon number 3. And obviously this is a methyl group. And so you're thinking, yeah, this one, if this amine wasn't there, all right, it would be methyl benzene, right? But then when you make it part of an amine group, recall I said, well, this is ammonia. Hope my pen sticks here, my ink sticks here, okay. All right, here's my ammonia like this. Right, what I've done is I've replaced a hydrogen with an aryl group. Now, if it was just methyl, you call this methylamine. And so because you've done it with an aryl group, this would be phenylamine. Like this thing here is phenylamine, but then you've got a group coming off it. So you got off the ring. So you've got three methyl, this thing up here, phenylamine. Now this chemist is about as complicated, as difficult as you need to be on the A level, all right? Now this one here, okay, I put this one in because anytime you have an alcohol and a carboxylic acid, all right, on a ring system, the carboxylic acid is always going to win. It's always going to be the highest priority system. And so therefore, without the OH, this would be benzene carboxylic acid. With the OH group on it, it then drops down into being in position 3, but the alcohol becomes a hydroxy. All right. So it's hydroxy because it's in second place, the carboxylic acid. So therefore, this becomes 3-hydroxy benzene carboxylic acid. All right. And let's see. Well, this one at the end, oh, yeah, this is your 2,4,6-trimethylbenzene. This is TNT, right? So carbon number 1, 2, 3, 4, 5, 6. All right. Now, again, the root, the base of this is methylbenzene, and then you've got nitro groups in carbon spot 2, 4, and 6. You've got 3 of them, so it's trinitromethylbenzene. All right. All right. Amides right here, last one. Okay. Now, on these, this is my N-propyl phenylamide. Now, you may be wondering, what's the reason for the N? Well, because what you're stating is that the propyl, the alkyl group to the right, the phenyl, the aryl group to the left, are attached to the nitrogen. Okay, and so it is just a way of making sure that everybody knows that the alkyl and the aryl, they're both attached to the amide group. All right, one on one side, one on the other, right? So, and the same thing here with the N-phenylbutanamide, okay? Now, I know, chemists, that we've covered a lot in today's masterclass, but hopefully what that was an introduction to arenes. All right, so we looked at the history of benzene. We looked at the stability of benzene. We looked at pi bonding systems, conjugated pi bonding systems. We looked at naming arenes, and we looked at the author meta para nomenclature. Okay, so next week, same time, what I'll do is I'll do we'll do reactions next week. Okay, we'll look at Friedel-Crafts acylation reactions with acid chlorides and with acid anhydrides. All right, so hopefully you found this one helpful. Have a good week, and I'll see you next time.